Değerli katılımcılar, değerli dostlar ve sevgili gençler, sosyal medya platformları üzerinden bizi izleyen ve izleyecek olan bilgisever, bilim dostu, güzel insanlar. Hepinizi en içten dileklerimle, saygı ve sevgiyle selamlıyorum. TÜBİTAK Temel Bilimler Araştırma Enstitüsü'nün seminer serileri, dünyanın en önde gelen üniversitelerinden harika bilim insanlarının katkılarıyla gerçekleştirilmektedir. Enstitümüz bu seminer serileriyle en üst düzey ve yenilikçi bilgileri ülkemiz ve dünya bilim camiasına aktarmaktadır. Ne mutlu bizlere ki bizler bu necip eylemin bir parçasıyız ve bugün bu vesileyle yine bir araya gelmiş bulunmaktayız. Bu sefer konumuz Newton'un deyimiyle en güzel sistem olan evrendir. Bugün Oxford Üniversitesi'nden son derece değerli bir konuşmacımızla Profesör Pedro Ferreira ile evrenin güzelliğini ve gizemlerini, kozmik uçurumları tartışmak üzere bir araya gelmiş bulunmaktayız. Seminerimiz İngilizce olarak gerçekleştirilecektir. Bu nedenle ben de İngilizce devam edeceğim. Dear participants, dear colleagues and friends, hello everyone and good evening. It is my distinct pleasure to let you know that this evening we have another wonderful episode of this inspiring online astronomy and space science seminar series of TÜBİTAK Research Institute for Fundamental Sciences, with the participation of Professor Pedro Ferreira from the University of Oxford, distinguished scientist and world-class expert in the field. He is going to give a great talk entitled The Cosmic Chasm. At the end of the talk, we will have a question-answer session where questions can be asked by sending a message through the chat button of the Zoom platform or just by raising hand. Pedro Ferreira is a professor of astrophysics at the University of Oxford and a fellow of Oriel College. His research focuses on the interplay between theoretical and observational cosmology. Throughout his research career, he has worked on a wide variety of topics: the origin of structure due to cosmological defects, the origin and evolution of primordial magnetic fields, the large-scale structure of space-time, such as topology and geometry, theories of dark energy and dark matter, techniques for analysis of cosmological data sets, the development of pipelines for cosmic microwave background experiments, and statistical methods in cosmology and astrophysics. Pedro Ferreira was born in Lisbon, Portugal, and attended the Technical University of Lisbon, where he studied engineering from 1986 to 1991. While there, he taught himself general relativity. Later, he did a PhD in theoretical physics at Imperial College London. He occupied postdoctoral position at the University of California, Berkeley, and at CERN, before returning to United Kingdom to join the faculty at the University of Oxford as a research fellow and lecturer. Here, finally, in 2008, he became a full professor of astrophysics. His most recent book, The Perfect Theory, is a biography of general relativity. It was shortlisted for the Winton Royal Society Science Book Prize and shortlisted for the Physics World Book of the Year 2014. He is a member of Royal Astronomical Society. Now, I want to thank Professor Pedro Ferreira for joining us for this seminar. Pedro, good evening once again and welcome. We are very happy to have you with us. Please begin your talk.
Thank you very much for your very kind words, Professor Aliyev. I'm delighted to be here, and I will try and get this going. I assume you can all see this?
Yeah.
Okay, well, thank you very much. This talk is going to be about how I see the state of play in current cosmology and how it's actually much more than just cosmology. It's really about fundamental physics. And I'm going to start with this image, which is in some sense one of the most boring astronomical images you could look at. This is an image of noise in the sky. This is a map of the relic radiation left over from when the universe was very hot and very dense. It's the light emitted when the universe recombined when it was at an age of about 380,000 years old. It's really a picture of the universe in its infancy. This is basically light with a wavelength of about 1 millimeter. And as you look at this map, what you're seeing is regions of more intense or less intense light. We often say hotter regions and colder regions. Hotter are the redder parts, colder are the bluer parts. This is basically the sphere unfolded onto a plane. Now, this picture of hot spots and cold spots has had a dramatic importance, as I will show you in our understanding of fundamental physics. And personally, it's very much connected to my career as a scientist. When I began science, when I became an adult in the scientific world, this data set had been released. So let me just add that this is the data set from the Planck satellite, the European Space Agency Planck satellite, and this map was released in 2015. I basically began working in cosmology actively on the release of this data set. This is a data set, the release of the COBE data, a NASA satellite. And what you can see is, again, what you see are blue spots and cold regions and hot regions, cold spots and hot spots, but it's much more blurred, much less focus on this. And let me just flip back and forth. Here you see a phenomenal amount of structure on scales of 1 degree. Here the angular scale is about 10 degrees. And this was transformational. The fact that we could see these ripples in the relic radiation of the cosmic microwave background revolutionized cosmology. And since then, we've progressed in a dramatic way. So one of the things you can do is you can get hold of this map and try and quantify how much structure there is on a given angular scale. You want to see if there's a lot of structure, for example, on 80 degrees compared to 30 degrees compared to 10 degrees. And often what we plot is something called the angular power spectrum. And one way of thinking about this is you can take the Fourier transform of a map on a sphere, and you can then calculate the power in this Fourier transform in each mode. So the L scale is in some sense, the Fourier mode. We call it the angular mode. But another way to think about it is it's the inverse angle. So in this area, we're looking at very large angles, and this area we're looking at very small angles. And this was the situation in 1995, shortly after the COBE experiment. COBE data is over here. There were a bunch of other experiments which were beginning to map out this variance of fluctuations in incredible detail. But this is what we had. Now, if we look at the 1995 map, we're going to look at exactly the same quantity. And in just under 30 years, we've ended up with this. This is 20 years, or almost just between 20 and 30 years. And again, this is the variance of fluctuations. This is the L that I had here. So large scales are over here. COBE would have detected over here. And this is small scales. And this is the Planck data. And I want you to notice a number of things. The blue dots are the data from the experiments. And let me point out that these blue dots have error bars. They have error bars, but the error bars are so small that they are smaller than the dots, the graphical dots. That's the first thing. The second thing is there is a red line going through it. And that red line is our best theory that fits this data. And the remarkable thing is that this theory has all this structure, these oscillations, this decay, this plateau over here, and it fits it beautifully. It fits it so beautifully that we can do the following exercise. We can subtract our best fit theory from the data and only plot the residuals around that theory, which is what is done down here. So if we subtract the best fit theory, we end up with these, from the data, we end up with these dots that scatter around zero. We can see the errors more clearly because we're zooming in. Look, the scale here was in the thousands, here it's in the hundreds. But the agreement is remarkable. It's absolutely remarkable. So we seem to not only have progressed dramatically in terms of our ability to map out this cosmological observable, we're also incredibly able to fit this theory with this data with a theory. Now, this is the map that I showed you. And so this is a snapshot of the universe when it was about 380,000 years old. But the current age of the universe is about 13.7 billion years old. And when we look at the night sky, we look at something like this. This is a map of galaxies. Each dot in this map is a galaxy. And so what you can do is you can point your telescopes at the sky, and wherever you see a galaxy on the sphere, you mark it down. And what you see is this remarkably structured map of, this remarkable map of large-scale structure. What you see is that the galaxies coalesce to form clusters. They'll form some filaments and walls, but you'll also have empty regions. In other words, the universe today, when we look at the light spread out in the universe, which is concentrated in galaxies, it also has structure. It also has these more intense regions and less intense regions. And so if you have a good theory of the universe, you should be able to link what the universe is doing when it's 380,000 years old to what it's doing now with a snapshot such as this. And we do that. And what we do is we take hold of our universe when it's 380,000 years old, and we evolve it forward. We have mathematical models to evolve it forward and to see what kind of a universe it would form today in terms of how galaxies are distributed. And this is done by some of my colleagues here at Oxford. It's a collaboration called the Horizon AGN collaboration. And this is exactly what they're doing. They take the initial conditions of the universe and they at the 380,000 years old, and they evolve it forward. And what happens is gravity starts to bring together the hot regions, starts to empty the denser regions. The hot regions coalesce and they form stars. The stars come together and they form galaxies. And these galaxies light up because they're these huge agglomerations of stars. But not only that, there's a lot going on in these stars because within these galaxies, you may have objects which collapse and explode like supernova, which send out these incredible bubbles of light and energy, which then will re-energize the evolution. And so this universe is this dynamical structure where you have these galaxies that you see on the screen moving around, coming together to form the structure in that map that I showed you before. So this link between the past, when the universe was 380,000 years old, and the universe today is another way in which we can link, we can learn about the fundamental physics which is at play when we try to model the universe. Now, this is the power spectrum again of that map. And the power spectrum of that map can be used in some sense as a fundamental physics, as an instrument to measure fundamental physics. Because by looking at this data set and looking at the theory, we can learn a lot about various things. We can learn, for example, how fast the universe was expanding and how fast it's expanding today. And we will come to that later on. We can learn about the geometry of the universe. When you look on very large scales, you should be able to detect whether the universe is Euclidean or not Euclidean. And we learn that basically by the position of this peak over here. We can learn about the components of the matter of the universe. For example, one of the things that is crucial is how many baryons there are, how many normal stuff, atoms, we call them baryons, there is in the universe. And we do this by measuring the relative height of these peaks relative to each other. We can look at, for example, the way that this power spectrum decays as you go to smaller and smaller angular scales. And that'll tell us not only about how ionized the universe was, but it'll also tell us something about the nature of the neutrinos in the universe, how massive they are, how many they are, what is the density of neutrinos in the universe. It's really a completely remarkable tool that can tell us about what the universe is made of and how it's evolved. It can also tell us about how the universe began. By looking at the overall structure of this, we can see what kind of evolution it must have had at early times to seed this structure. And we end up with this canonical and well-established image of the universe. We know that the universe has been expanding. It's been expanding. It was very hot at early times, but at some point, hydrogen formed, i.e. first of all, at very early times, nuclei would come together to form the lighter elements. At a bit later time, free electrons and protons come together to form hydrogen. And what this means is the universe undergoes this transition from a charged plasma to a neutral plasma, and light is free to propagate until now. This is the cosmic microwave background that I've been talking about. As you wind the clock forward, this hydrogen starts to coalesce and starts to form the first generation of stars. This first generation of stars will then coalesce to form will collapse, new stars will be formed, they will come together and they will start to form galaxies. And these galaxies will then form the tapestry that we see today. So there's really a lot going on. And the beauty of this is this on the whole can be completely described by the theory that we know. And one of the things that I find amazing is that in some sense, every now and then we hear about people talking about the theory of everything. What is the theory that describes the everything in the universe or everything around us? And we have a theory of everything. And the theory of everything can be written down in an equation like this. And this equation basically has a number of components. The first thing is it's a quantum equation. And it's a quantum equation, so this is what is known as a path integral, where you have to integrate over all the different types of degrees of freedom you have in the universe. It's the physics of Heisenberg and Schrödinger. It includes gravity, so it's an integral over space-time where you have to include the fact that there's a dynamical metric and that the gravity is described by the Einstein-Hilbert action. This is the mathematics of Einstein. The fundamental forces are described by a Yang-Mills field. It's the theories of Yang and Mills. We have that matter is described by fermions, which are coupled in a particular way. And this is the physics of Dirac, and then the incredibly successful model of Weinberg and Salam. And we have a way of generating masses for the leptons. And this is the mathematics that Peter Higgs presented. But basically, we have an effective field theory which describes the universe, and it is a de facto theory of everything. We already have a theory of everything that describes everything that we see. And this is a huge success for fundamental physics. Of course, that's not completely true because cosmology has shown us something else. Cosmology has shown us that there are these open questions that we can't explain with that theory of everything, which explains just about everything else except these fundamental questions. The first thing is, when we look at the cosmic microwave background and we look at the universe, it has a particular structure, which at the moment, the simplest theory that seems to explain it is a theory in which the universe expanded or accelerated at very early times. It's what's known as the theory of inflation. And we don't have a clue how inflation happened or what might explain it. All we know is for the observations to work, we have to add in an ingredient, which is inflation at early times. There are alternatives, but all of them involve adding extra ingredients like inflation. Not only that, when we look at the data, when we look at galaxies and the structure of galaxies, but actually when we look at the large scale structure, the universe seems to be full of some form of dark matter. That is matter that clusters, that comes together to form the galaxies, but doesn't emit light. And again, we have no idea what this dark matter is. And we really don't. For decades, we've been pursuing different ideas, and we simply haven't a clue what this dark matter is. But there's more. When we look at late times, the universe seems to be expanding in an accelerated way. And we can't really explain this with the theory of everything that I presented. There has to be something else. There has to be something that is making the universe accelerate at late times. And the current way of packaging that is to say that there is some form of dark energy which takes up about 2/3 of the total energy budget of the universe. And that is what is driving the universe to expand. So this is the reason I called my title, the title of this talk, The Cosmic Chasm. We have this huge gap between the theory of everything, which explains just about everything, and these things, inflation, dark matter, and dark energy. And there is no way to bridge this chasm, no way to go from the theory of everything at the moment and these fundamental open questions. We simply haven't got a clue how to solve them. Nevertheless, it's been remarkable what we've done over the last 30 years with all these cosmological observations, and we're pushing forward. And so how do we push forward? Well, the first thing is, let's think about the cosmic microwave background. What these things are, these are instruments that look at the sky and they measure radiation with a wavelength of about 1 millimeter. And so we need to measure this radiation better. And the way to do this is to build better experiments. So what we do is we build better detectors that are more sensitive, that can pick up weaker light, but we also pack more detectors into each instrument. So this is a plot that was produced in 2013, which shows how the sensitivity, and this is basically the sensitivity to the cosmic microwave background, has been improving and will be improving over the next decade. And basically what you see is you pack in more detectors, and more sensitive detectors, so you can measure better and better the cosmic microwave background. And a particular example of this is the Simons Observatory. This is an observatory which is being built in Chile in the Atacama Desert, which would basically lie somewhere over here, which will produce remarkable maps of the cosmic microwave background, which will improve dramatically the quality of the maps compared to Planck. So that's one of the ways, better maps of the microwave background. The microwave background has taught us so much about the universe. We should try and pursue and do a better job. But another thing we can do is to try and make better maps of the universe today. We want to make better and better maps of the distribution of galaxies. And so this is a plot that shows you what you need to do for that. The first thing you need to do is you need to cover as much of the sky as possible. So you really need to see as much of the sky as possible so you can cover as much of what we call the cosmic web, pick up as many galaxies in all directions so that we have a complete picture of the sky. But not only that, we need to have detectors or telescopes that can see fainter and fainter galaxies. This means we need to be able to pick up galaxies that are further and further away. So not only do we cover more of the sky, we cover deeper into the sky. We look deeper into the sky. And this just shows how different experiments, current experiments, are doing there. And one particular example is the LSST, now called the Vera Rubin telescope, which lies over here and over here. And this is, again, it's a telescope which is being built in Chile, which has beautiful skies and which will be able to map the universe to incredible precision and pick up many tens to hundreds of millions of galaxies. It'll produce the cleanest snapshot of the universe today, of the recent universe yet done. Now, these are all terrestrial missions, but of course, one of the things you need to do is to go into space. And why do you go into space? Well, you go into space because we have the atmosphere, and the atmosphere complicates things. There's weather. More recently, there's the challenge of all these constellations of telecommunication satellites, which are going to populate the sky and are going to make it much more difficult to make precision measurements of astronomical or cosmological things. And so these are two examples. On the left, we have the Euclid Satellite, which is a satellite which is being launched by ESA in the next few years. And what this satellite will do is, again, try and make a map of as many galaxies as possible over a large slice of the sky. So we're able to get a better image of what the universe looks like now in terms of its distribution of galaxies. Another example is the LIGHTBIRD mission. The LIGHTBIRD mission is a satellite which will be launched by the Japanese, and it's going to be run by JAXA. And it'll try and make a map of the cosmic microwave background and try and dig down and see, for example, if we can find signals of that period of inflation. In particular, it'll be looking for gravitational waves from the very early times, a signature that inflation would have happened. So as you can see, this whole strategy is to do what we've been doing, but better, build better instruments which are more precise, which can map out the universe, and even better, in the hope that we will be able to bridge this chasm, in the hope that we will be able to bridge the separation between the theory of everything and these open questions. Except, and this is, I've moved backwards, except I have a real worry, and my real worry is that by going down this route of making these better and better instruments and better measurements, we won't bridge the chasm. My worry is that the result of this way of doing cosmology and fundamental physics is that we will get ever more precise evidence that there is something called dark energy, and ever more precise evidence that there is dark matter, and ever more precise evidence that something happened in the early universe like inflation. But it'll tell us nothing about what is the dark energy, or what is the dark matter, or what led to inflation. In other words, it'll make our ignorance incredibly precise. We will have a very precise understanding of what we don't know, but we will not solve the problem. We won't answer these questions. And so for a number of years now, I've been advocating that we need to think differently. We need to look at alternative ways of trying to bridge this chasm. And I'm going to talk about three ways ways we might do this. The first thing is to look at current problems that we're having with cosmological observations. So one of the things that you might want to look at, and that we've all learnt in our undergraduate physics, is the expansion rate of the universe. We know Hubble's law, and Hubble's law tells us that if we look at distant galaxies, they are receding, on the whole receding, with a velocity which is linearly proportional to the distance for galaxies which are reasonably close by. And this is Hubble's original plot. Well, not his original plot, his original data set. And what you have is, it really is a scatter plot of galaxies where, with some wishful thinking, you draw a straight line through it. Thankfully, we're not in this situation anymore. In 1995, you can go away and do the same calculation, and again, plot distance against velocity, and you plot Hubble's law, and you see that the galaxies fall straight onto this line. And so things have been improving dramatically. It's interesting to see over the 60 years or 70 years between the two plots. This is a state of play in 1962, and this is Sandage, who compiled different measurements of the Hubble constant, and what the different ways of measuring would give you 113 plus or minus 5, 75 plus or minus 25. Look at how discrepant they are and how they are inconsistent with the errors. The errors are small, but 113 plus or minus 5 is in no way consistent with 75. And this was the situation in the 1960s. What we find ourselves now is in a similar situation. We find ourselves now in a similar situation because this is the current table of constraints of the Hubble constant. And what you have is really two different types of measurements. You have what are known as cosmological measurements, i.e. measurements using, for example, the cosmic microwave background, large-scale structure, where you get a Hubble constant of around 67. But then you have more local measurements, looking at, for example, supernova or lenses. And what you're finding is that you have a measurement of the Hubble constant around 74. And so what you really have this incredible spread. At a time when we thought everything was converging, there is this spread of measurements. And it makes you think that maybe there might be a hint in these measurements. They could be systematic, there could be systematic problems, but maybe there might be a hint of something which might tell us what is going on in the universe. Hang on. Sorry, this is another example of that, a more reduced version, where you have the cosmological measurements are this black blob over here. This is H0 over here. And these are the local measurements with Cepheids. And what you find is at some point, they start to deviate. As the errors become tighter and tighter, they don't converge. And this is another data set, and they're all discrepant to some extent. So you might ask yourself, and there is a bit of an industry trying to figure out, what is the Hubble constant telling us about the universe? These discrepant measurements, is it telling us more? Is this giving us a clue of what might be going on? Another example is when you look at the amplitude of clustering, when you try and quantify how much clustering there is in the universe, how much structure there is on a given scale, you can do plots like this, which is you can constrain your best fit model, and it'll give you basically a contour, an error on the amplitude of clustering versus the matter density. And what you find is different data sets give you different results. So the cosmic microwave background is giving us a higher amplitude of clustering and evidence for more dark matter and baryons. While, for example, looking at local galaxies and the way that they're lensed gives you lower matter density and lower clustering. And this discrepancy is very difficult to understand. We really don't have a firm understanding why this is. It can't be explained by our current model of the universe. And it can't be explained by just positing the existence of dark matter and dark energy. Is this telling us something about what is dark matter and what is dark energy? And one of the things you can do is just try and learn a little bit more about what is happening here. And so this is a plot of over time. So where we normally quantify time in terms of redshift. So going back in time is along here. And this is the amplitude of clustering. And you can try and identify where is this discrepancy, or where is the discrepancy between this data. The blue line here is the CMB measurements, and this is all the late time measurements. And what you find is that around redshift of 0.25 to 0.5, you can see this very clearly, this discrepancy. So one of the ways is just trying to figure out, can we just drill down and figure out what is going on? So this is looking at cosmological data, but I think we have to be bolder. I think we need to look at things that we would not look at usually. And so one particular example is, instead of looking at the large scale structure, which is built of galaxies that come together, we should look at galaxies themselves. And the reason to do this is dark energy and dark matter, they are basically these extra degrees of freedom in the universe. They're these extra fields, these extra quantities. And they can play a role in the way that things interact with each other. They will be coupled to different things. They will be coupled to different components. And they might affect, for example, how the gravitational force acts. So the gravitational force, the gravitational potential is normally Gm over R, but often, and for many decades, we've spoken about the possible existence of fifth forces. And so what we can imagine is that we have the normal Newtonian force, and then we'll have a correction, which is delta G, which will, so this will add a correction, it'll change G, but you might also have a Yukawa term. In other words, it cuts off at a certain scale, and it's only valid in a certain regime. And for many decades, there have been attempts at making precise constraints on these different quantities. And this is from a review by Eric Adelberger, where he puts together all the different measurements, laboratory constraints and geophysical and astrophysical constraints. And what you can see is that you can place quite tight constraints on these corrections on a range of scales. But there are two things that we need to worry about this plot. First of all, evidence for dark matter and dark energy appears on very, very large scales. So in this direction, the first thing. The second thing is that in many of these theories of dark energy and dark matter, what can happen is that these fifth forces are screened, are suppressed in astrophysical or close to heavy objects, or for example, in the solar system, but they may play a role on very large scales. So you need to think differently. How are you going to probe these fifth forces on very large scales? These fifth forces, which will be a manifestation of dark energy and dark matter. And we've been advocating for a number of years that you should look at galaxies themselves. So this is a picture of the Milky Way. This is an artist's rendition of the Milky Way. It's a spiral galaxy. It has these arms. It's rotating around. It's quite messy if you look at it. You know, there's all this structure here. And it's quite complex physics because we know that there must be dark matter in it, but there are also atoms and baryons. There are baryons. There are things exploding. It's not a simple physical system. This is even clearer when, for example, you look at radio frequencies. This is a picture of the center of the galaxy taken by my colleague Ian Hayward using the very recent Meerkat radio telescope. And what you can see is a cacophony of stuff. You have bubbles, gas bubbles, you have magnetic fields. It's an incredibly complex system. And so you might worry that taking galaxies and using them to probe for other physics, for fundamental physics, might be a lost cause. Except, as we move forward, we've been making better and better pictures of more and more galaxies all across the universe. And there are a number of things that you have to notice. First of all, this is a mugshot, a snapshot of a compilation of galaxies from the Sloan Digital Sky Survey. And they all look different, but they all look quite similar. They all have a certain structure. And they all have a certain structure. And if you can focus on that structure and try and see how that structure doesn't interact with all the complexity, you might learn about something about where these galaxies are lying. So, for example, suppose you take a galaxy, and this is a rendition of my simple rendition of a galaxy. A galaxy, our current pictures of galaxies is they live in halos of dark matter, and you have here the disk with the stars, okay? And normally you have them sitting at the center of halos. But if you have a dark energy which is coupled differently to the disk and to the halo, as the galaxy is moving forward in this dark energy bath, the disk will feel different forces compared to the halo, and they will be pushed back gravitationally to the center of the halo, but they'll feel also, the halo will feel these extra forces. And so this displacement will affect the disk, and it'll have two effects. There will be an offset between the disk and the halo, and there will be, the galaxy will be warped. It'll be folded slightly. It will be bent slightly. And what you can do is you can go and look at catalogs of galaxies, of hundreds or thousands of galaxies, and see where they lie within the halo. And you, for example, you can use gas as a proxy for where the halo is, and see if there's some correlation in the way that they're deformed and the distance from the halo and the overall gravitational field on large scales. And the remarkable thing is that you can actually get rid of all the complexity. If you have enough galaxies, you're looking for a very small signal, but a very small coherent signal. And so you can basically use all these galaxies and look for this small coherent signal in this very large but uncoherent noise. And you get something like this. You can constrain the strength of the fifth force using these galaxies. And what you can find is you can find incredibly tight constraints on scales of megaparsecs. And this plot is important because basically this plot shows that for particular models of dark energy are completely ruled out, because if you wanted them to lead to the acceleration of the universe, they would have to lie, this fifth force would have to be at this level, and it can't be. It's completely ruled out. So this is the first example of using galaxies to really learn about dark energy and eliminate a lot of possible models of dark energy. Another example is, it turns out that black holes satisfy particular properties, properties in that they don't couple to the dark energy in the same way that the galaxy will couple. They satisfy what are known as no-hair theorems. So if you have this large bath of dark energy and in an environment where you have this screening that I mentioned, you'll have that the galaxy will be moving in this field in a different way from the black hole, and the black hole will be displaced from the center. And so by looking at how black holes are displaced from the center of galaxies, we might learn something about these dark energy models and the fifth forces that arise from these dark energy models. And the thing is, over the years, there have been compilations of black holes and their offsets from galaxies. So one of my graduate students was able to go through the literature and compile this beautiful plot where this is the displacement in kiloparsecs from the black holes from the center of galaxies, and this is redshift. And what you find is that you've got this wealth of data that you can work with and try and pin down. Again, it's a coherent signal which you want to extract from an incoherent noise. And we've done this, and again, we find now, looking at a different class of dark energy models, we're putting constraints on the strength of the fifth force, which means on the type of dark energy models which are allowed. If you just look at one particular black hole, M87, you get this constraint. But what my student Declan Bartlett showed is that you can actually put these remarkable constraints on very large scales, which is exactly the scales that you are worried about for the acceleration of the universe or dark energy. So this is a particular example where you use objects that you would never think of using to try and understand about dark energy and dark matter, and try and figure out and use them to probe different regimes and see if you can learn something. As I go into the end, the final part of my talk, I'm going to talk about something that you've all been exposed to. This is a beautiful sketch by Kip Thorne, one of the theorists, but one of the fathers of experimental gravitational wave physics. He surmised that if you have two black holes and they orbit each other and they come together, they will inspiral, they will merge, and they will settle down into a final black hole. And if you look at the gravitational waves, they'll have this kind of almost universal form. You'll have this oscillatory form. Then something will happen over here, which at the time he didn't know. This sketch was done in the 1980s. And then it'll settle down and you have a ring down. And so he said we should go out and look for this signal. And they did, of course. And they built an instrument, LIGO, to go and do that. And this was their announcement in 2016 of their detection in 2015 of such an event, where indeed you have some kind of merger, and then you have some kind of in-spiral merger, and then the ring down. And so this is really the beginning of gravitational wave physics. This is over time, and the blue line is measured with one set of detectors in Livingston and in Louisiana, and the other one is Hanford in Washington. Now, since then, a lot has happened. This is a recent plot, which lists all the detections of binary mergers. And so over here, you have the masses. And what you have is this person has basically plotted, you start off with two black holes here that merge to form a black hole here. And we've learned so much from looking at this. First of all, we've learned about what black holes look like, what the populations of black holes look like. We've realized that certain things that we took for granted about what types of masses were allowed or not allowed don't hold, that black holes in a certain regime, which we thought wouldn't exist, do exist. So we're really learning a hell of a lot about compact objects, black holes, and astrophysics. But I would argue that we can learn more. We can use these to learn more. We can use these to learn about dark energy and dark matter. And so a particular example is, suppose that you're able to measure a black hole, a merger, and you measure the gravitational waves coming from this black hole. But you're also able to measure some event which is tied to that merger, which emits light. So it could be black holes merging, could be neutron stars merging. And so you can have this one event and you can measure the gravitational waves coming from this, and you can measure the light coming from this. We can time them and we can see if they take the same time or if they take a different amount of time. And if they take a different amount of time, we can place a constraint on the difference between the speed of gravitational waves and the speed of light. Now, it turns out that for a large class of dark energy models, gravitational waves will feel the dark energy like a medium, which means that the speed of gravitational waves will be slower or faster than the speed of light. So if we are able to measure the speed of gravitational waves and compare it to the speed of light, we are able to put a constraint on this dark energy medium. And this is indeed what happened with an event in 2018, where they were able to measure a merging binary, a neutron star binary. They were able to measure the gravitational wave signal, but they were also able to measure the light emitted associated to that event in lots of different frequencies. And what they found is that the arrival time between the gravitational waves and the light was within a few seconds. They were able to work out the distance of this object, which is about 40 megaparsecs, which means that they were able to place a constraint on the difference between the speed of gravitational waves and light to be about 1 part in 10 to the minus 15, 10 to the 15. So they are almost identical. The speed of gravitational waves is almost identical to the speed of light. And that immediately is able to place dramatic constraints on what kind of dark energy we are allowed. We're really honing into what we'd be allowed to consider, what we should be looking at if we're trying to figure out what is the dark energy. But I think we should go further, because black holes are these very interesting objects. They're in some sense. John Wheeler used the relativist John Wheeler used to say that when you want to explore a physical theory, you should look at its extremes, because that's where you see the cracks. And I think the black hole is an extreme object where you might want to do this. So one of the things you might want to do is, if you have this black hole sitting in this dark energy or certain types of dark matter, it'll accrete, it'll do something. And this is a simulation by one of my graduate students showing what happens if you have a Kerr black hole in a bath of, for example, an axion field or a massive dark energy model. And what you see is that it basically accretes and it forms this very complex structure. It forms this complex structure at which you could probe somehow. But more importantly, this complex structure will affect the black hole itself. And which means that when we see a merger, when we see a black hole formation or collapse, this might affect the gravitational wave signal. You might be able to look at how you might be able to learn from the gravitational wave signal something about this type of dark matter or dark energy. Not only that, black holes will live in this dark energy or in this dark matter. And as they move forward, they will form wakes. So this is a simulation by another of my graduate students, Dina Trekova, who's now at the Albert Einstein in Berlin. And this is showing what happens when you have a black hole moving at relativistic speeds through this bath of massive, either very ultralight dark matter or ultralight dark energy. And what you form these wakes, not only will it slow down the motion of the black hole and it'll affect its dynamics, it'll form these intricate patterns in this stuff. And so the question is, can you go out and look for this? Of course, ideally, what you want to do is you want to look at mergers, because that's the things that we're seeing, the thing that we're seeing with LIGO. And so this is a rendition of a snapshot of a simulation where you have two black holes immersed in this dark energy or dark matter field. And you get this accumulation around the black holes, but you also get some structure around it. So he's done a simulation here of what happens. And so this is two black holes orbiting each other and slowly coming together. And as they come together, they collapse, and you have these waves of dark matter and dark energy, which in turn interact with the gravitational waves. So you can imagine going in and looking for these signals. So how would you look for these signals? Well, this is an example of how small these signals might be. So over here, it's the gravitational wave amplitude. And what you can see is that this is after the black hole has formed. It emits what's known as the ring down, that last bit of Kip Thorne's plot. And what you have here is the blue line is just the normal stuff, imagining that there was no coupling between the black hole and the dark energy. And this is if you couple it a little bit, and if the coupling is not very large, it's at the 10%. And it's very difficult to distinguish between these lines. But if the coupling is just a little bit larger, you'll be able to distinguish between what you would get if you had just pure GR and these red lines. This red line is what you get if you have this coupling to the dark energy. So these are very faint signals, and it's very futuristic, but you might manage in being able to do that, for example, in 20 or 30 years' time with something like the Lcdm satellite mission. Now, I've been focusing on black holes, and just for my final transparency, this dark energy and this dark matter, they have a structure it has structure, and it in itself might form compact objects or objects which collapse to produce interesting gravitational effects. So this is a simulation which was only produced yesterday by one of my postdocs. And what he's looking at is what happens if, for example, your dark energy field is not just a scalar field, but it's a complex scalar field. You can form these structures called cosmic strings where you have concentrations of dark energy, which then evolve and collapse. And the result is quite remarkable. So this is the cosmic string, and this is what we're going to look at is the radiation, which is either emitted in pure gravitational waves, massless scalar, and massive scalar. And so what you see is as the cosmic string collapses, you emit these gravitational waves over here, but you also emit this radiation here, and you emit this massive scalar radiation. It looks very different. If you were just looking, you might be able just to look at this and try to figure out if there was some signal of dark energy. But the fact is you're going to have all these other channels, and especially this will feed into the scalar part of that. So you might have all these different ways which will tell us something about the theory that we're trying to understand. So I'll finish here. I think we have an incredibly successful theory of fundamental physics. I've said that I believe firmly in this, that we have a theory of everything. And it's the theory that we teach our students, and it's the theory that we use in almost all of physics. Cosmology has shown it is incomplete, and there are these open questions. And there is this massive cosmic chasm between the questions, the things that we can explain with our theory of everything and the open questions in cosmology. Now, we've come to this situation because we've been very successful in cosmology. We've mapped out the universe with exquisite precision and with remarkable detail. And so we're going to do that. We're going to build better instruments which will look better and harder. But I think there is a risk that all we will do is we will just understand our ignorance better, but we will not understand the problems. We will not solve the problems. And so I think, and I've been advocating for a number of years, that we need to think differently. We need new explanations, we need novel analysis, and we need different experiments. We need to look at the universe in a different way if we're going to solve these fundamental problems. If you want a lay explanation or a lay expose of what I'm advocating for, you can click on I've written an essay for Eon, where I've explained this whole philosophy behind what I'm advocating. But I think I will end here.
Thank you very much for this very exciting and comprehensive talk. Please, we can now pass to question answer session, yes?
Yes, of course.
Yeah, please ask questions, sending us using chat button or just raising hand your questions. Indeed, we have received several questions by email. Pedro, may I address you these questions?
Of course.
Yeah. So first question is the following. What can we say at present about ultimate evolution of the universe in terms of Einstein general relativity, as well as other theories of fundamental physics? Indeed, you talked a lot about it, but nevertheless, there's questions about ultimate evolution of the universe.
I need to understand, there are two different ways of answering that. First of all is when the person who is asking me ultimate evolution, does it mean how the universe ends? If that is the question, I think more than ever, we have no idea, and I don't believe we will ever know what will be the ultimate evolution of the universe. Whether the other part of the question was with regards to Einstein's theory. So Einstein's theory of general relativity is remarkably well constrained on a number of scales, first. Second, Einstein's theory of general relativity is what we used to make these calculations in cosmology. And as I showed you, the plots, the comparison between theory and data is remarkable. Nevertheless, there is still freedom. And it is possible that Einstein's theory of general relativity might break down on large scales in a way which is unexpected. I have yet to see an example where I think that it's an interesting proposal, but the constraints on Einstein's theory of general relativity on large scales are still not as strong as they are, for example, on astrophysical scales or in the laboratory.
Mm-hmm. Thank you. The next question is the following. What's your forecast for the resolution of the current discrepancy in the measurement of the Hubble constant? Can one consider this discrepancy as signaling a new physical property of the universe, or just unrecognized measurement uncertainties?
So I think I alluded to that in my talk. I think we need to look at that carefully. At the moment, my hunch is that there is some systematic discrepancy, and I don't know where. I don't know if it's in the CMB measurement. Mostly someone coming from my field would say that there's a problem with the local measurements, but I don't want to say that. I don't understand at the moment. There are a few things that I don't understand. Nevertheless, I think it's a useful exercise to try and figure out what implications such a discrepancy might have for fundamental physics.
Mm-hmm. Thank you. So one question came also through the chat button. How do you measure the offset of the black hole from galaxy center?
That's a really good question. And I think different observers do it in different ways. So I wouldn't want to give you a complete answer. I could point you to the literature, but you would look at, first of all, you look at velocity dispersion, local velocity dispersion in the galaxy. Often what you do is you do it in an indirect way, which is you try and reconstruct the gravitational. What you do is you measure velocities of the galaxies. You take a picture of the galaxy, right? And you measure the velocity flow in the galaxy. And then you try and reconstruct the gravitational potential. And you have a black hole as one of your parameters and its position. And it is from that you infer, from the potential that you infer, that there has to be a source with a certain mass in a certain location. So I think that would be the generic answer to your question. Nevertheless, I think different people do it in different ways. I think that's a general principle, but they do it in different ways.
Mm-hmm. Thank you. Another question is there a real need for the moment for additional physics beyond the standard Lcdm model?
Is there a real need? So the answer, so there are many ways of answering that. Let's assume there isn't, okay? There are still open questions, right? So if you assume that it's lambda CDM, you have to understand why lambda is so small. So at the moment, the current physical model doesn't explain that. Second, part of lambda CDM is the DM, the CDM. We don't know what CDM is. Yes, you need new physics because you don't know what the CDM is. And for decades, people have been advocating supersymmetric partners. There are now other alternatives, but we definitely need new physics. To get the initial conditions for the lambda CDM universe, you need a particular type of scale invariance in large-scale structure, which has been advocating inflation. Again, you need new physics. You need to advocate some type of energy in the universe, some type of scalar field. So lambda CDM is a new physics model.
Thank you. The next question indeed is in a sense continuation of this, which states that there exists a rigid opinion that in question of the universe, at least for the moment, we have not gone further than Einstein's theory of general relativity. What do you think about it?
I think I repeat my answer, which is Einstein's theory of general relativity is perfectly consistent with cosmological observations of the universe, because we can explain things in terms of some extra component like dark energy or an inflaton field. But if you take these observations and you are agnostic and you try to place constraints on Einstein's theory of general relativity, the constraints are weak. And so you either, as a matter of principle, say, yes, but it's Einstein's theory of relativity, that you're perfectly allowed to do that, but you are not doing that based on data. You are doing that based on opinion.
Mm-hmm. Thank you. The next question, perhaps a bit is philosophical than physical. In modern understanding, the notion of time and simultaneity is relative. That's true. And this is proved both theoretically and experimentally. Then, can one think of time as illusion in the fundamental description of nature? Pedro, I don't think that time is illusion. Nevertheless, please, your opinion.
I'm afraid that sounds like quite a philosophical question, which is outside my range of expertise.
Yeah, that's true. So, any other questions, please? So I don't think more questions. So if there are no questions, no more questions or no comments, perhaps we can stop here, Pedro. Will you please give your final remarks? Thank you so much for this very nice seminar, and please give your final remark.
I don't really have anything to add apart from thanking you personally for inviting me to do this. It was a pleasure, and I hope one day to visit Turkey because I've heard it's a really fantastic country. So,
thank you very much. We will be waiting to meet you here in person at our institute in our activities, seminars, or summer schools. It will be a great pleasure for us indeed. So we will be looking for meeting you here. So when this COVID disaster finally resolves and leaves the world. Thank you once again so much for this seminar. And take care of you, please.
Okay, thank you very much. Thank you. Bye-bye.
Thank you. Bye-bye.